Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody from the future. Today is special because we're actually done with the material. I told you everything that I had to tell you about big data, so you have everything you need for the exam. The guest lecture last Wednesday was all approved, so you have the recording on YouTube, you have the slides on the Moodle. And today I'm just going to wrap up. I'm going to give you a high-level overview to make sure that you see how the pieces assemble together, because everything we saw is just part of a big puzzle and it all fits. I would like to make sure that you do have this high-level view on what we've done. And then I'll talk about the exam a little bit, and then we'll play a game. We have, which one? Do we have other TAs in the room? Maybe they joined and said, yeah, I thought you said half of the team was coming. Maybe they were scared because I told you your brilliance, and they were scared to lose. With the otherwise, it will be you. Maybe you can still send a message to see if a couple of them can come. We'll see. All right. This is how brilliant you are. You know, they were so impressed that they thought, okay, no, we're scared of losing against the students. All right, so let's start. So I would like to come back to a list of the top 10 that I already gave you actually in the middle of the semester, but now I'd like to go through this again with the perspective of everything we've seen during the semester. So the first thing that I told you is that it is extremely important to learn from the past. And this is actually so important because a lot of people are doing the mistake. And in fact, if you look on social media, you have a lot of influencers that post videos that have or documents that have millions of followers. But a lot of them just see through, you know, Python, pandas, and that's it, right? But that's not the big picture. There's much more out there. And in fact, a lot of the principles that have been invented in the 70s for relational databases, they also apply to big data. The notion of data independence, the notion of having a query language, functional declarative, the notion of optimizations, and so on, it still applies. It might not be tables. We see that there are other shapes out there. It might not be SQL. We saw that there are other query languages out there, but the principles are the same. And not seeing that has a cost. It has a cost in productivity and a cost in performance, because if you don't pay attention, you select the wrong database, the wrong shape, you don't respect data independence, you're going to have something that is slow. And if you do not use a query language, but you try to re-implement a join, then you're going to lose in productivity, because you need to re-implement something that already exists, right? That you get for free with any query language. And in fact, it happened a lot, I noticed, with document stores, right? Because systems like MongoDB do not support joins. You can select, you can project, you can aggregate. And a lot of people end up implementing a join in C++, you know, connecting to MongoDB, and they have their own join. But the thing is, a join should be implemented once and for all in an engine, like PostgreSQL has this. A lot of engines have the join, and the join, when it's implemented just once by specialists, they really do it like clockwork, you know, in terms of performance. So it's going to be much better than doing it all over and over again. And there's probably 1,000, maybe tens of thousands of implementations of joins on top of MongoDB because of that, where it would be just simpler to take an existing engine that exposes you at the right level. It's just an example. Something else that I have observed from not learning enough from the past is with XML and JSON. There's a tendency in recent years that JSON took a little bit over from XML, so it's growing in popularity. Do not underestimate XML. It's still widely used in the corporate world and by governments for data, so it is actually there. It's important to know it. But what happened historically is that at the beginning of JSON, a large part of the JSON community, sadly, rejected XML. Like it was built like, oh, XML is too complex. We know better. Let's just build something simpler. But what happened year after year is that all of the components of XML were actually just reinvented in JSON. It would have been so much faster to learn from XML and take it over, simplify, of course, but take it over to JSON. We would have been years faster if we had actually done that. Because if you look at it, JSON now has schemas, just like XML schema. It has query languages. In fact, it has 30 of them. I'll come back to it. It has the notion of pointers across documents. There are even documents in JSON that have namespaces. So we believe that it's only XML, but no, namespaces are everywhere. And so in fact, all of the principles are exactly the same. So this is what I want to say. If you learn from the past, if you look at what people have done before, it can save yourself a lot of time, a lot of money to actually not reinvent something that already exists, and to benefit from the experience of earlier engineers and researchers, right? All right. So tables are not going to disappear, of course. For a lot of use cases, relational tables are perfect. In fact, if you work later in a company, it might be tempting to use the super cool new technologies, but a lot of the time, all you need is a table, and all you need is a relational database management system, and that's fine. You know, they are 50 years old, they are super good at what they do. In a lot of cases, it will fit on a machine, and that's all you need. But it's very important to understand too, that in some cases, the data is not shaped like a table. It can be shaped like trees. We saw that this is what happens if you denormalize the data. But we also saw that in some cases, you want to look at your data as a graph. This is if you have to traverse what would be a lot of joins in a relational database management system, you can replace with navigating through pointers in memory with graph databases. We also looked at cubes, data cubes that allow you to have a whole business-friendly system to slice, dice, roll up, and so on. And each shape has its own flavor and its own life. And if you understand, when you deal with data, which shape it has, then everything will just come into place. You'll have the right syntax, the right language, you're going to be productive, and you can pick the right systems. And it's getting better every year, right? It took a while at first. I mean, if you go 20 years ago, there was barely only tables that had implementations, but now a lot of the shapes, I will come back on that, almost all of them now, no, all of them do have query languages, syntaxes, and so on. It's all done now in 2023. Design principle number 3 is keep the design simple. And if you look at what we've done in the semester, it very often happens. In particular, we had the key value model at a lot of places. When we looked at, for example, HDFS, what is HDFS? Just a bunch of directories and files as a hierarchy, and every file is just a list of blocks. That's it. It's super simple. DynamoDB is just a key value store, so you just associate values with pairs, and you have a limited size for the values. S3, it's the same. It's just key values, right? You upload and you download files, maximum 5 terabytes. It's the power of simplicity, because when you have something extremely simple, then you can multiply this in billions or trillions very easily. You can, when it's simple, you can also spread it across machines very easily. So keeping the design simple is very important when you deal with large quantities of data, right? So I like this quote by Albert Einstein: everything should be made as simple as possible, but not simpler, of course. Something that's directly related with simplicity is the modular stack. I showed you this perhaps every week, this modular stack. As computer scientists, it probably is not going to surprise you, right? You are used to modularity in a lot of languages. You build like this, like a Lego game. In fact, it has to do with the fact that we are only humans and our brain can only do so much at the same time, right? So this is why we all have different jobs. We specialize in different things. And it's the same here. If you look at the big data stack, nobody knows everything exactly, right? There are people who specialize in storage. They know everything that there is to know about HDFS and cloud storage. There are other people who know about query languages. There are other people who know how to implement Spark from scratch. They would be able to build a system that is massively parallel. There are other people specializing in schemas. There are other people specializing in large language models. We'll see that also comes on top of the whole stack. And then there are people specializing in hardware, right? They can build CPUs, tensor processing units also. And all of that works because at every level in the stack, you have an API, an interface with what's above and what's below, right? You build on top of what's below. So relative to where you are, what's below is the physical layer, and where you are is the logical layer. But if you look upwards, the people above are your customers. They are using your system. To them, you are the physical layer. So you see that this whole thing about data independence, logical, physical, is relative, right? the logical layer, you're the logical layer to what's below, and you're the physical layer to what's above. This is how it works. It's kind of also the design by contract of programming, but taken to an architectural level, right? So this is why we have this modularity. It also makes the learning easier because every week we just looked at a single level. Every shape, now I already said that, but every shape has a paradigm. Data models can be several models, maybe not just one, but several competing models, syntax, query languages, architectures, and we can even map between the shapes. For example, so these are the shapes, right? 5, cube, table, tree, graph, bunch of text. Cubes, you can slice, dice, aggregate, and so on. Tables, you can select, project, rename, and so on. Trees, you can also look up, navigate, down and up, normalize, denormalize, validate, and so on. You can also select, project. Graphs, you can traverse, you can find patterns. The match clause is so important in query languages for graphs, right? So you can find patterns and then select, sort, and so on, because we saw that even in graph databases, you have the same good old clauses as for trees and tables, where, group by, and so on. That also exists. But the match clause is what you add in a graph database system. And bunch of text, this is not covered in this lecture. We did it for some of you in information retrieval. You can still filter, map, group, and so on. You can compute statistics over text, right? So every shape gives you specific things that you can do, and then you get to think logically about it. You have syntaxes. For cubes, you have XBRL. For tables, you have CSV. For trees, you have XML, JSON, YAML. For graphs, there's Turtle, RDF over XML, and so on. Text is already by itself syntactic. So you see, all the data shapes have particular syntaxes. They also have languages. We saw that cubes have MDX, even though we didn't really cover it. I just mentioned it. Tables have SQL. Trees have JSONic, XQuery. JSONic is just the XQuery for JSON. And then we have AQL, Nickel, Uncle, Particle, GraphQL, and so on. For graphs, you have Sparkle, Cypher. I also put GraphQL because probably that's the intent, but I consider GraphQL to be more of a tree query language. A bunch of text, that's also what we covered in information retrieval. You can have the Boolean query language, actually. If you Boolean search could be considered a language by itself also. But you see that by using the right language, you're basically directly manipulating the data as it is. Then we saw, and that's again the power of simplicity, is that if you want to have terabytes or petabytes of data, you should organize things in such a way that you have quadrillions or trillions of the same thing seen from far away, right? So homogeneity in the large. So trillions of the same thing. But if you zoom in, and I'll come back to that, then it's heterogeneous again, right? It's just from far away. And in fact, when you have homogeneity in the large, this is how you manage to fix this problem. This is where the lecture started, right? We have this mismatch between the capacity that grew so much and the throughput a bit less, and the latency, it's even worse. And so we learned that for the capacity and the throughput, we need to parallelize, and between the throughput and the latency, we need to batch process. Exactly. Now you understood that, right? And you can do that, parallelize and batch process, because we have trillions of times similar objects, right? So this is what allows us to scale out, you know, the collections of trees. We can just spread them all over machines by just making sure the trees are not too big, right? Roughly 10, 20 megabytes maybe for each tree, but then you have billions or trillions of them. However, if you start zooming in and looking at the individual objects, they're all different, right? It's actually what you get when you denormalize data, because you have no schema. So you might have extra fields, you might have missing fields, you might have nestedness and so on. And that's okay, because with the power of polymorphism, with object-oriented languages, we can actually implement that quite well. And in some cases, when we actually clean up the data and validate the data, we do end up with homogeneous collections. And then we even saw that then you can use data frames and you can be even faster, right? So the idea is that if it's heterogeneous, you can handle it also on the high level. If it's homogeneous, then you can start optimizing things below. It's invisible, it just gets faster, right? If it's homogeneous, then it just gets faster and takes less space in memory. Right, so this is how we got from tables to collections of trees. Who now has the feeling that it's very intuitive to them, right? We denormalize tables, we get collections of trees. Who has the, yeah, awesome, perfect. I like to see that. So this is one of the big intuitions I wanted to give you in the lecture, that we denormalize tables to collections of trees. Now, if you zoom in, you're going to see all the data types, in particular the atomic types. And here it can be a big mess, really, because if you look at the whole landscape of technologies, I showed you a few, but there are others. The names are not the same and so on. However, it's still more or less the same. You're still, whatever you look at, you're kind of going to have decimals. You're kind of going to have integers, maybe several of them, byte, short, int, long. You kind of have an IEEE 754 version of double or float in some way. It might be called differently, but you're probably going to have it, floating points. You always have strings one way or the other. You always have Booleans, binaries, but again, it can be hex or base 64, depending on the implementation, maybe even others, but still a sequence of bytes. And then you're going to have dates, times in various flavors, maybe with, without time zones, and so on, right? But you still kind of have them, even though they are called differently. And then in terms of structure, you typically have lists and maps called objects and arrays, but again, depending on the language, it's different. The one thing I want you to see here is not so much that it looks like a mess, is that actually if you zoom out, it does not look like a mess because it's really always more or less the same types. Who has this intuition now, right? Awesome. So if I give you now any piece of technology that you don't know, a schema technology, a syntax, and so on, you can look at the documentation. And in fact, you in 5 minutes, just skimming through it, you will not even need to read in detail. You skim through it. Oh, yeah, that makes sense. Oh, there's doubles here, there's integers there. You basically know that on the high level. That will make it much easier for you to learn all of this. Just a matter of looking at the documentation, right? Speaking of that, schema technologies, there's plenty out there. They are more or less work the same. You basically have some syntax that you parse to memory, and then you can validate it to check that it has a specific structure. Then you get, on the one hand, a yes-no answer. Either it's valid or it's not valid. And the second thing you get is called an annotation. It's the idea that once you have validated and you know that something is a date or an integer, then you can optimize the footprint in memory of the date or the integer, right? You can store them much more efficiently. And think data frames, basically. A data frame is just an optimized version of a homogeneous sequence of trees. Then we separated the abstract logical model for the physical implementation. It's all connected, right, with also with the technology stack and so on. That's data independence. You always have a logical implementation on top of a physical implementation. Always remember that when you build technology that has to do with this, always think, what is my physical layer, what is my logical layer for the perspective of what you're building, and then nicely encapsulate and separate the layers. For example, we saw that you can implement cubes on top of tables. Then the cubes are the logical layer, and the tables there are the physical layer. That might have sounded surprising at first, right? Because we always saw that tables are logical, right? And then it's what you write in C++ or Java that is physical. But actually, tables can be used as a physical layer on top of which you can implement other shapes. So you can store cubes as tables. You can also store tables as trees. In fact, this is easy because you know that a table is just a flat, a homogeneous collection of flat trees. And then you could basically, you could simulate a relational database system on top of MongoDB. You could implement SQL on top of MongoDB for the case where the data is flat and homogeneous, right? It would be, of course, maybe less efficient to abuse MongoDB in order to implement a relational database management system, but it would work. It would work, right? We can also store trees as graphs because trees are just graphs without cycles. Again, it wouldn't be efficient, but you can do it. You could also store graphs as tables, for example, with 3 columns, right? The origin, the property, and the destination, subject, property, object. So basically what I'm saying here is you can in fact store any shape in any other shape, right? You can always see a shape as the logical form stored in another shape. And in fact, when people implement a new kind of system where somebody discovers a new shape, for example, vector databases are quite in trend at the moment. Typically, the first implementations are not going to be from scratch. The first implementations are going to reuse an existing system on top of it, and then try to get the best of it. At some point, it's going to reach some limits. It's not possible to make it faster. However, you will have gathered so much experience from that now you can go ahead and implement it from scratch and natively, right? And then what you do is you just swap the physical implementation, but you keep the logical API. So this is extremely powerful. That it is at the same time extremely powerful, and people get it wrong. The number of times that I have seen people use MongoDB to store tables. You shouldn't. You should be using a relational database management system, or people using a graph database also to store tables. You can always start tables in a graph database. But if what you want to do is just selection projection, then a graph database is going to be slower than a relational database management system. So always ask yourself, what is my shape? What is my model? And then pick the right system. In the end, ideally, you would always end up with a fancy declarative language on top of some physical hidden implementation in the style of MapReduce and Spark, and then some hidden storage that you are not supposed to see if it's well encapsulated. That's something I showed you in the first class, just in the same way that there's assembly code and high-level languages. We can consider now that the APIs like Spark, Pandas, I'm also putting Pandas in there, the MongoDB language in JavaScript, these are all like assembly code. And then you have the high-level languages like SQL, XQuery, JSONic, GraphQL, Cypher, MDX, and so on. These are the high-level query languages. They are to Java what these APIs are to assembly code. What I did not show you is, of course, it's out of scope, but we have the same for machine learning. You have all these libraries, TensorFlow, PyTorch, and so on. In fact, they are only the equivalent of assembly code. I don't know yet what this is going to look like. People are trying. Declarative ML is being researched, but I hope at some point we are going to have the equivalent of Java and SQL for machine learning, and you will not even have to write and use any API like that. It will be used, of course, but it will be hidden from the user with a high-level language. I think this is the future. So we use RumbleDB in this lecture, the goal of which is to showcase that all of these pieces of the puzzle come together. Then we sharded the data. We did it the whole semester. We did it for HDFS, we did it for MapReduce, we did it for MongoDB, and so on. That's something that comes very naturally at large scale. You just shard the data and distribute it all over multiple machines, right? It's a common thing to do. And the twin brother or sister of shard the data is replicate the data. Every shard is stored multiple times. Now you know that there's a lot of names for that. Shards, blocks, splits, chunks, and so on and so on. It doesn't matter how it's called. You're going to see new system, maybe they come up with fancy names. Still the same, it's a partition in the end. So replication of the data is to avoid if there is a natural catastrophe or something, then you have multiple copies, then you have a backup, and the system is going to continue to work. That's with the CAP theorem, right? You continue to be available because you have multiple copies. This is also very important. That's probably also one of the lessons that hopefully you learned in this lecture is that we have a lot of machines, thousands, tens of thousands of machines in the data centers, and we just spread the data and we spread the computations all over the machines. And now you know how it all works with the mapping, shuffling, and so on and so on. You know the whole secrets of massive parallel processing, how that actually works. It really alternates between mapping, shuffling, mapping, shuffling, mapping, shuffling, mapping, shuffling. For every stage. We saw that many times, and the only exception I think was DynamoDB, we had a centralized architecture. We had somewhere a coordination and then worker nodes. It was the case for HDFS, for Hadoop, for MapReduce, and so on. You just need to learn the names, but it's basically often the same. It does lead to a few bottlenecks. We did see that. We also saw a few ways to mitigate with, for example, federated HDFS, where you have multiple coordinator nodes. You can have also standby nodes and so on, right? But more or less, the entire semester, we saw that this kind of architecture is actually quite popular for big data technologies. And something that we also looked into is batch processing. It's really this idea of avoiding the latency. If you process your records one after the other, you can come back in 1,000 years and it's still not done. So the secret is to batch process. You process 1 million records at a time, then you take another 1 million records, then you take another 1 million records. That's how you do it. And in fact, a comparison that I can give you is imagine that you want to upload, you have a website hosted somewhere on a server, you SSH yourself there, and you want to copy, maybe with SCP, you want to copy, let's say, 1 million files that you want to upload. So you might first try to upload file by file, right? You write some scripts, some bash script in order to upload the files, but then you're going to see it's very slow because at every file, it's again having the latency of sending the file. What's the secret? You create a tar.gz, and you send a single file over the network. It's super fast. That's exactly batch processing. When you create a tar.gz file and send it over the network as a single file, you are in fact batch processing. That's exactly the idea. All right. So all of that, all of these principles will allow you to make design choices. So you can look at it from the perspective of this pyramid right here, where in many cases, you learn an existing product. It already exists, so you just take it, you read the documentation and use it. I've shown you a few examples, but there's many other products out there, but they really work in pretty much the same way. Then at the second level, you have to choose which product to use. Maybe you're going to be working in a company, you have data to store and manage. Now you know how to choose the product. Look at the data. What shape does it have? Right? What does it look like? And then you know what category of products to look at. Then you can choose it. And some of you might even design new products, maybe as researchers, maybe as engineers in companies. But I'm pretty sure you are going to invent new products that don't even exist. And maybe in 10 years, they will be taught in universities. This is exactly what happened with Hadoop, HDFS, MapReduce, and so on. They were at some point invented by smart engineers, right? And so I think that's the whole idea of teaching, right? It's just a chain, right? I learned all of that from people who did it previously. Now I'm transmitting that to you. You are going to invent, and maybe some of you will teach it to the next generations and so on. And then we just get better and better and better at developing these products. So you need to ask, okay, what's the shape of my data? How much data do I need to store? Is it just a gigabyte? Then just use a laptop. That's enough. Is it petabytes? Then for sure you need to use a data center. Maybe it's a terabyte. Do I need a data center? It depends. If it's bound by how fast I read from the disk, then yes, a data center might actually help. If it's not a problem with that, but with the CPU, then maybe that's not a good idea, right? So now you can make this kind of assessments too, depending on the size too. And then what do you want to do? Do you want to project, select, slice, dice, and so on? It changes everything for the choice that you make. And what you really, really need to do, and this is this thinking critically, critical thinking is kind of the DNA at ETH that we want to transmit to you. When you are about to implement something new, like you just open your favorite code editor and you are starting to write code, always ask yourself, wait, am I just reinventing the wheel, like recoding something that people already have done before? Try to avoid that. Always ask yourself, has it been done before? Can I just not reuse it, right? Very often that's the case. And this is really this idea of, I really love this quote, you can have a second computer when you can use the first one. So really always think like, can you fit it all on one machine before you use a cluster of machines? That's kind of what we analyze with parallelism and batch processing. So in fact, we solved that discrepancy between capacity, throughput, and latency. Now, what does the future look like? So I tried to make a few predictions a few years ago, and I kept them because some actually happened, which is really great. This one has not fully happened, but I think that MapReduce and Spark in the end will become invisible. Like the engineers, like you will know about them, but the end users, if they use query languages, they don't need to know about these things. They just use SQL or similar languages. And all the rest, Spark and so on, happens in the background as a compile version of the query. Data shapes will be central. This is really something that I hope is going to happen, because this makes such a big difference to realize that data has shapes and to think about the models. But I have the feeling that this is getting more and more mainstream, this idea that it matters, because more and more systems now explicitly sell themselves as a specific shape. The query languages are invented now for really specific shapes. It's a graph language and so on. This is going in the right direction. New shapes, maybe. I gave you 5. It might be that there are new shapes. You always need to ask yourself, is it really a new shape? For example, right now, vector databases, right, or multidimensional arrays with machine learning. Do we need new shapes for this? So we certainly need new hardware, right? Like tensor processing unit and so on. Is it a new shape? I haven't made up my mind yet. Maybe it's a new shape, maybe it's not. Maybe you can just consider them also as with arrays of arrays or with tables. I haven't made up my mind yet, but I'm slowly leaning towards the fact that these might be new shapes that might be needed to be added to the list. But it takes a while. This all needs to mature, and we will learn more in the years that come. Then I hope that the query languages will get standardized. SQL, it's already done. Last Wednesday, I actually learned from, at the same time as you, and I was really delighted to hear that there is this SQL/PGQ standard. They finally standardized this whole thing. Like Cypher, Gremlin, PGQL, and so on. Now it's been unified as a standard called SQL over PGQ, and it seems that everybody is now aligning. So for graphs, we've won that battle. We have now a unified standard for querying graphs. So that was really something I was very happy about to see last week, these developments. And the nice news is that it's very close to what I taught you with Cypher. It's really based on something like that. Might have a different taste, but the big picture is exactly what I have taught you. Now, that's not the case for trees. And in fact, I like to show this with what happened in the case of trees. You probably know this comics. Who knows it? Who see what's coming? Yeah, some of you. So the situation is that there are 14 competing standards. Actually, now we are already at 30 plus, but anyway. So there's all these competing standards. And every couple of months, in some company headquarters, I have to show you the standards. So for example, this is the actual state of the art, some of the languages you have for trees. JSONic, we were very early, it was already more than 10 years ago. Now you have AQL, Uncle Nickel, SQL++, Miracle, JSON Query, GraphQL, JQ, Jackal, JSON Pass, SPACule, and so on and so on and so on. It keeps growing bigger and bigger. And the reason it grows bigger and bigger is that every couple of months, in some company, always another company, there are people who realize, oh, we need a language for trees. But instead of looking up the existing languages for trees and the standard, they just invent a new one, or they want to unify the existing ones. And then you get a fancy website that pretty much looks like this, like, oh, we revolutionized everything and have this cool new language. But what you actually did do is you just added one. And now you basically have this list. I try to keep track of them, but it grows bigger and bigger and bigger every time. I had the hope, really, when we did JSONic, the goal was, it was already a standard. JSONic was based on XQuery. XQuery was designed by SQL editors. There was people from Oracle, from IBM, from Microsoft, from plenty of companies that contributed to it. So the hope was really that since so many people from so many companies were involved in the design of the expressions and so on, but somehow it hasn't happened yet. I still hope maybe in 5 or 10 years, I can give some good news that we finally have a unified standard for querying trees. But whatever it's going to be, again, more or less, it's going to be similar to what I've taught you. It's only then a matter of aligning with the standard that we're going to get. Then we saw cubes, where you can do these fancy reports, except that that's not what I wanted to say on this. I wanted to say that in the end, a lot of users do not even write query languages. They don't even write SQL or anything. They just use some UI. In fact, I told you the pivot tables in a spreadsheet software to slice and dice. You don't need a language for that. You just drag and drop this. Who tried it? Who opened the CSV file as a pivot table in a spreadsheet software and tried to slice and dice? Nobody? Oh, yes. Okay, awesome. You should. Sorry? It came up today? Ah, awesome. So now you have a reason to do it. Awesome. So please do the exercise and do it. You will really learn a lot. So this is a UI, it's a user interface. So yes, so it should become the norm in the end. In fact, it's even better than that. And that now really has happened and is happening even more since actually 1 year now, is that now we have all of these large language models that add text on top of this. The direction in which I sense this is going is that a large language model by itself is not enough. It will not compute properly, it will hallucinate and so on. However, I think it's going in the direction that we do have the large language models that kind of interface with us with words, but connected to an underlying knowledge base or an underlying system, then that can actually be a very powerful combination. It's still ongoing. I don't know where this will go, but I could totally expect that this way of just speaking to the machines might be one of the possible futures that we will live in. Of course, it doesn't invalidate the rest. You will still need all of these technologies. They will just be behind, right? So the engineers will still have to build these things, but a lot of people will just speak to the system. By the way, this idea of talking to machines was already present in Star Trek. There was, who saw the Voyage Home, Star Trek? It's very funny. It's a very funny movie. And so basically they have to travel back from the future. And then there is this scene in which one of the people from the future is in front of a computer, one of the ATs, grabs the mouse and starts speaking in the mouse, like, computer, do this and do that, right? And this is actually, they already saw that, but this is exactly what's starting to happen now. Then data might become fungible to the point that you can actually look at data like some sort of molecules that can flow. And in fact, this is kind of happening with Spark and MapReduce in the way that it flows. But with technologies like XBRL and RDF, this is the direction in which it's going. So fungibility is really the idea that you can spread it interchangeably over the cluster in order to query. This is a very abstract way of saying it, but I sense that this is also happening. It's also happening in the context of blockchains, right? When you store data on some blockchains, the notion of who owns the data and so on and so on. But anyway, it's very blurry because this is still ongoing, and I don't know where this will converge. Data and money will converge now. It's kind of already happening. The fact that bits can have value as a distributed ledger. This is not a recommendation to buy anything. You should really distinguish the technology with the actual value. What I mean here is really the technology, the fact that it solved an actual problem in distributed computing to agree on who owns what. Then there's data protection. That is actually incredibly important, and it gets important every year. You cannot ignore that, especially those of you who are data scientists. You have to think about that. You learn all of these technologies, gives you a lot of power, but you do need to be careful that that data might be about people. And so this is why now a lot of countries or regulators are starting to put some framework to that. Now there is this funny thing happening that machine learning, it used to be just done on top of text and CSV or hard coding in Python. Now more and more machine learning is sitting on top of database systems, which is great. But what's funny is that it's also happening the other way around, is that some people are actually replacing the components of a database with machine learning. And one example that I really love to show, it's done at MIT. One of my colleagues who actually did his PhD here at ETH, so the idea is that for indices, we saw B+ trees and hash indices, right? Remember that. Well, you can throw that away and replace it with a machine learning model. You train the model on how good it is to look up something, and then you just use the model in order to actually look it up. So you just remove the B+ tree, the hash index, put a machine learning model instead. So it's actually quite powerful. It seems to work quite well. So this is also the sort of things that is happening. Then there is quantum computing. It's very uncertain, basically, the way it's evolving. So right now is exactly the period when you need to be careful. Why? Because everybody's talking about it, there's money flowing into it, and you have a lot of noise. The thing is that we do seem to make progress in the number of qubits that we can process. There are a few unknowns. We don't know if we are going to hit a wall. It might be that at some point there are physical reasons why we cannot process or keep in coherence more than a certain amount of qubits. We just don't know. We have to try. Another problem is the noise. That you actually need, I think, maybe 1,000 physical qubits for just one logical qubit in order to solve that. So it's actually very costly. Just so who already knows about quantum computing? I think some of you already. Who doesn't? Okay. So let me tell you briefly what's the differences with classical computing. So in classical computing, a bit is either 0 or it's 1. Then you process with AND or NOT, you can process with logic gates. In a quantum computer, it can be a superposition of 0 and 1 with a certain weight. It can be a bit 0 and a bit 1 at the same time. And basically, all the computations, they happen on a superposition. Like, for example, if you have 3 bits, then basically you have a combination. 3 bits basically encodes the integers from 0 to 7, right, on 3 bits. If you have 3 qubits, that's basically a quantum superposition of 0, 1, 2, 3, 4, 5, 6, 7. It's a superposition of that. So then when you put it through the gates, quantum gates, what's happening is that you compute on all of these at the same time. You calculate the evolution on every possible qubit. So it seems like you're doing everything at the same time. Sounds very powerful, right? But there is a catch. The first catch is that at the end, when you're done having your superposition, then you run your calculations on everything. At the end, you only get one result, only one. You cannot get all of them, just one. That's the first catch. It would be nice, right? If you got all of them in polynomial times, that's it, P equals NP, right? Yeah, in terms of performance. But there's a second catch, is that not only do you only get one of the results, you don't even get to choose which one. It's drawn randomly with a measurement. So there's a lot of catches that basically seem to limit what you can do. And yet people have managed to implement, for example, prime factor decomposition on top of a quantum computer using qubits and Fourier transforms, a quantum version of that. And then you can do it actually in much more efficiently than you would on a classical computer. So it seems that in some cases you can. In all of them, we don't know. So we don't know yet if all NP problems can be efficiently implemented on a quantum computer. This one is an open problem. We just don't know. And so yes, so now there's a rush towards quantum computers because it has uses for example, pharmacy, chemistry, and so on. So there can be a lot of applications. Anyway, I just wanted to say that there might be some research to do when it's mature for databases. How do we then store data on top of these quantum computers? Okay. This is an interesting paper that ties relational databases with quantum computing from University of Oxford, Samson Abramsky, for the curious. And then there's where this is all going, where this is actually some things you find in scientific, let's say, popular science books. Are we actually turning the whole universe into a big computer, right? As we build structure and structure and structure, and when maybe once we'll explore other galaxies, I don't know. But this leads to basically very interesting philosophical questions on what is computation, what is computational ability, and so on and so on. And here the quote is, "Information is physical." The idea that whenever you speak about information, in the end, it's stored on atoms and molecules. Yeah. All right, so it's going to be the break now, but I would like now a big applause for the TA team who's been serving you this whole semester. So Wei Xuan represents them here. Oh yes, and you're here too, yeah. Come here. So thank you very much. So the two of you will participate in the quiz against this. Yeah, you can continue to applaud, they deserve it. So that was an awesome team. Really, really great work. All right, so let's take a break. And then after the break, I'll talk about the exam and then we'll play the quiz game. I will explain everything. And there is actually some chocolate, that I will share with you, at least with the winner. So see you in 15 minutes after the break.